Okay, Elainna, I'm back. I'm not at school anymore. I'm at home, and so you're probably going to hear dogs' claws ticking and, I don't know, jingle bells jingling in the background. I decided to just not deal with your TA's notation until I have more information, and instead show you my solution using my own notation, and then I think we'll be able to see the acceleration conclusion, same conclusion that your TA made for acceleration, and then the same conclusion that your TA made for tension. If I can read the handwriting correctly, his tension says his final equation for tension is m1 m2 over m1 plus m2, and then I think it's a 2 times 1 plus sine of theta, and then the acceleration is g times quantity m2 minus m1 sine theta over m1 plus m2. So I'm assuming that theta refers to the angle of incline here, the alpha, that we maybe switched angle notation, and so we'll figure it out as we go. I may have to stop and restart the video and post it in between because I'm not sure how much data I can post at a time. So I'd actually already started this recording. It's been a busy week and a busy day, as I kind of mentioned. My robotics team is doing a presentation at the Maker Faire in Thanksgiving Point, and we had to load up the vans and stuff, so that ended up taking longer than I expected. In any case, I'm here now. So I realized that I mislabeled one of the blocks. This is S2, I think, according to the TA's notes. I'm looking, so I printed out your TA's blackboard, and I have that with me, so I'm kind of referring to that as I go. And then S1 is the block on the incline. I think we're good now. Okay, so I mixed these guys up. I mixed my notation up. In any case, I'd said when I thought I was recording but had no sound that the first step, whatever the notation is, the first step is a free body diagram. So we look at, yeah, right? This is S2. Okay, oh my gosh. So we look at the hanging block, S2, I hope S2 is the hanging block. And there is the upward tension and the downward pull of gravity. And the downward, let's see, I can't not use your TA, so we'll call this W2 for the weight of block 2. And we might even, immediately sort of substitute M2G because we know that quantity. We know that the pull of gravity, at least in a flat Earth approximation, is M2G, right? The flat Earth approximation means we ignore curvature of the Earth. We assume that pull of gravity is always straight down to, or I should say maybe perpendicular to a flat ground level. So I don't think we have any indication of the relative masses of these two. Your TA's notation that up the hill should be positive kind of makes me think he or maybe the problem is indicating that S2 is larger than S1, but we're not sure. So for my first guess, I'm going to say that the weight of block 2 is larger than the tension, that the weight of block 2 is larger than the weight of block 1. And yeah, well, let's just do it that way for now. Okay, so then S1, the hanging block, only has two forces acting on it. There's only one contact force, and then we're, at this point in mechanics, only considering the pull of gravity for a field force, right, for a force that acts through a vacuum. And then for S1, we have also tension, and I'm going to try to follow my own rules and make it, the same length as the tension in the free body diagram for block 2, because the string or rope is massless and non-stretchable, so we assume that the rope just serves as a way to transfer the force from one object to another. And then we have the normal force, so the support force of the plane holding up S1, on the plane, and then again the directly downward force of the pull of gravity. so W1, which again I can immediately write as M1G. Okay, I can't help myself. I keep looking back to your TA's Blackboard notation, and I can't help myself to just keep trying to figure out what those symbols are meaning. So I'm going to, for the time, assume that the weight of block 2 is larger than the weight of block 1. So I tried to draw weight 2 larger than weight 1. Actually, I will check your TA's diagram for that. Now your TA draws tension and weight vectors looking awfully like the same, and that can't be the case, because if that's the case, this is a static problem, and it's not even interesting. So we'll go with a longer weight, shorter tension, same tension in the pair of diagrams, and a shorter weight for block 1. Okay, so we have our free body diagrams. Because we have a block on an angle, the next step is to decompose the vectors so that they lay in a coordinate axis that is parallel to the direction of motion. So we want to overlay an axis on our inclined block that runs parallel to the plane and then anti-parallel to the plane. So, and this is where the Z goes, right? Z up the plane. So we're like assuming that the blocks are going to rotate in the counterclockwise direction. So we can call it Z, we can call it whatever we want, right? This could be X prime. I don't really care what we call it. Let's call it Z just for kicks, right? So that's our new like X axis. We're totally reimagining Cartesian coordinates here. And then I can't tell what up the plane. It looks like he's calling that X, but I can't tell. I'm just going to call it Y, because why not? No pun intended, but also that's pretty funny. So Z up the plane, Y perpendicular to the plane, and again, it doesn't matter what you call them, we're just saying it makes sense to choose a coordinate system that's parallel to the direction of motion, and then coordinate axes have to be perpendicular to each other, so parallel versus anti-parallel gives us in the direction of the normal force. Okay, so in AP Physics we went through a ton of practice kind of figuring out these angles, but you can kind of extend the vertical weight vector, and then you can extend horizontal, and this becomes our plane here. This becomes our angle alpha. So our angle alpha is reflected here, right? They're similar triangles. Our angle alpha is the angle between my negative y-axis, that I'm calling this y, my negative y-axis, and the weight. So now I can decompose this weight vector into its components that are trying to pull the block down the plane, and the component that's pushing the block into the plane. So I'm going to say, so the tension is in the z direction, done. The normal force is in the y direction, done. But I need to talk about the component of my weight vector, weight 1, that's in the z direction, and it's actually in the negative z direction, and that's cute, whiz. And then I need to talk about the component of my weight vector that's in the perpendicular to the plane, so we just call it 1y, right? And your TA, like I'm trying to not look at the notation, but your TA is using some kind of unit vector notation to indicate this. I'm using subscripts. Subscripts, unit vector notation, it all means exactly the same thing. It's all trying to be super clear about direction, right? And especially direction in terms of this funky coordinate system that we've imposed on the inclined plane. Okay, oh dear, I've been talking for 9 minutes. Okay, so I'm going to stop and upload this, and then I'm going to record again.